Hello, ladies and gentlemen. The Earth is aerodynamic. That's the title of this one. Here's why. I'm going to go ahead and zip down here. It's going to take me a little while to go through this one because I'm going to start talking to folks about how do you figure out the different angles of things you see on the landscape and in the sky. And, the U.S. artillery has got a pretty good way of doing it, and that's how we're going to figure out what it is we want to figure out, which in this case is going to be the obliquity of the solar system in relation to the galactic plane and a few other things to mention as well. And so I'm going to go ahead and start right here with my PowerPoint. Here's my PowerPoint, and this is going to be the one that talks to us about Mount Rainier. Mount Rainier is such a beautiful mountain. As you can see right here, I'm using Google Earth right here, right? And right here I've got this funny looking little mountain peak. And it's the funniest thing that somebody, and this somebody is David Morrow. David Morrow is one tough guy. And to tell you what, he is an excellent photographer. And I would take any of his photographs anytime of the sky. I'm not sure if he chose this one particular setting because of the the unique way that it appeared. I don't know, because he doesn't strike me as being a soldier or anything like that. So I don't know that he was thinking in terms of using Mount Rainier as a sight aperture. I am. So as we see the draw right here between this mountain peak and the summit of Mount Rainier, right down here is about where the galaxy comes shooting up. I'm not going to show you Mr. Morrow's photograph directly, and the reason that is because I don't want him to get mad at me. But I do know that we have a galaxy photograph from this man, and I used his photograph to figure out the basically the galactic angle in relation to Mount Rainier and our planet. That wasn't an easy thing. It took some time. But to do that, I had to basically calibrate a retical pattern. So I traced a retical pattern off of some magazine somewhere that I found on the internet that actually had military settings on it. And military meaning it covered mils. And mils are what the artillery use to determine range and deviation. Deviation is your ranges in meters from your left to your right. So they don't necessarily work for, range in terms of distance, because depending on the angle of the terrain as you're looking out, distance can be different as you look through your binoculars or whatever sighting device you happen to be using, right? So right here is the photograph, and we're not going to go into that. So you can see how that it looks like Mount Rainier is erupting. Maybe that's what he was thinking. It looked like it was erupting the galaxy or something like that. He takes some. I just love the photographs. If I had more money, I'd be buying every photo that dude makes. He's a tough guy. He's out there hitting the ground, living out there, living it rough, and free as a bird. But he takes some really good photographs, and he sits he might as well be a freaking photographic sniper. He sits there and waits for the perfect target. All right, going on, enough about Mr. Morrow. I already clicked on that slide. And so basically I'm taking Mr. Morrow's view here, and I recreate that scene after having had so many years experience in, observation posts and things like that, looking for Inamahoonimoonies. This is one where I can easily figure out almost exactly where Mr. Morrow was standing, and I would call it the Morrow OP. And I could get you the same exact view just right here. I guarantee you this road right here looks just like the road does in the real photograph. So, then you got to take your elevation here. But to calibrate, you got to go somewhere. So I found this point over here, believe it or not, that point right there where you see the crosshairs of this reticle pattern. It's actually 1,000 meters distant from the position I'm standing at down here where you can't see, because the height of my view as you are looking at this screen is at my eye level, not at my feet. So it doesn't really matter when you start to measure things in terms of meters, it's close enough, right? And so basically the elevation is what I'm going to take from where my feet are standing. And then I figure out what that elevation is, and I go ahead. Oops. Mark is at 3,000 meters distance. My bad. The mark right there, the red one, is at 3,000 meters distance. All right. So maybe I couldn't get a... This was quite a while ago. Look down here. What's the date? May 9, 2018. Yeah, it was a long time ago. I'm sitting here trying to figure out what I did. Well, normally, if you go at a distance of 1,000 meters, right, your tick marks are set at 10 mils apart from each other as increments. And so at a distance of 1,000 meters from the position you're standing on, every 10 mils or every tick mark is 100 meters. Every 2,000 meters distance from where you stand, that tick mark now represents 200 meters, so on and so forth for every additional 1,000 meters distance from your position. So this one is at 3,000. I guess I just went ahead and decided to figure out what 100 meters would look like from that point. Now I'm going to go down here. Oh, that's another... Oh, I went up. Excuse me. Now right here is where we're looking at the top of Mount Rainier. Oh, hey, you know what? That's a volcano. Oh, I don't know if I would have figured that out if I didn't have this picture right here to tell me that's a volcano. All right. Well, anyway, I'm just being sarcastic based on something someone said. Okay, so here's my little marker down here for Sunrise Point where Mr. Morrow would have been standing. And go to the next slide down. Okay, well, I didn't really use this stuff here. This is a photograph from Ethan Tweedy. Yeah, I didn't use that one. Okay, yeah, but you can see they're using lasers to... This is at this facility. Forget where it was, Hawaii or something. Yeah, Mauna Kea. Okay, now here's another spot. Here's where I am measuring distance, and so to measure the distance I have to figure out where the terrain feature is over here on Mount Rainier, which is the saddle between that one mountain peak to Rainier summit, and that being my sight aperture. So I'm calling that point the center of the galaxy. And then of course Sunrise Point is here, then I draw a straight line going through there, and Google Earth tells me what the direction I am facing is, which is observer target line 222.5 degrees. Now, when I'm measuring this out based on Mr. Morrow's photograph, this isn't the only measurement I've ever taken. As a matter of fact, I went outside my house in Spanaway once, and I don't own that house anymore. And I went in my driveway, and there was a really good way to, for as much as you can get it with all the light pollution, I was still able to get a fairly decent idea of the galaxy in its relation to Spanaway, Washington. So I shot an azimuth, and go figure. It came out to about 222 degrees. So it's like, okay, well, it looks like we're talking about the same thing right here. So I decided, I'm going to stick with that. There it is. And then down here, of course, is my reticle after I calibrate it. And based on the information I just gave to you. Now I'm going to go to my other slide over here. This is how I apply my reticle pattern. I enlarged the green pattern thing here so that it might be easier to see. And then I have the 222 degree line, observer target line, which is going back here, which is the brown one with this color of goldish brown. And this is what I refer to as the observer direction to galactic plane. So this is our galactic plane coming out there, right? And then I have the tangent from known point 1 is 76 mils. So when we're looking out into outer space and we look at a specific part of the galaxy, which was only visible on Mr. Morrow's photograph, there was a particular spot on that galactic view that not only could I see it in his photograph, but I also could see it in the panoramic photograph that I showed in one of my other videos that shows the entire, as a compilation as well, it shows the entire span of the galaxy. And maybe I haven't presented that one yet. In fact, that might even be this video. I don't know. Anyhow, what I'm trying to say is, there's a known point out there, and this is the direction to it. So, 76 mils is equal to 4 degrees. Okay. 1 degree is like 17.4 mils, so on and so forth, you see, because there's 6,400 or 6,400 mils in one circle, as there are 360 degrees in one circle, right? So there you have it. And now you know why there's so many more tick marks on the mils than there is on the degrees, because it's got to be a heck of a lot more accurate if you're throwing an explosive round down range and you want it to actually hit the target. All right, so current elevation of my, of this position that I was looking at across from me is the same elevation that I am standing on, and I'm looking at it right here, and that's at 6,552 feet above mean sea level, MSL, and Mount Rainier side aperture is right there. Hey, that's funny. That don't quite seem to be... Well, I guess it wasn't that mountain peak there then. This mountain peak over... Wait a minute. Did I do something wrong? Watch me do something wrong. Let's see, where was it here? No, I didn't show that view over here. No, I get it right. I can see it in the photograph here. Oh, so my side aperture point was just a little bit off. As in my description, right? Okay, so we're over here. Okay, it wasn't that mountain peak. It was just a little right here. That's so unsubstantial. Oh, how disappointing. Well, anyway, it still works that way. So this site is set correctly. Yep. I did this on October 6th. No, I didn't. This is based on the photograph of David Morrow that was taken on October 6, 2012. All right? Because naturally, you know, as the years go by and the different days and times are between photographs, it may not always be at this point, from this observer point, right? So our galactic angle is at a negative 4 degrees. And that's what we're reading right here to our tangent, pretty sure. And the vertical angle is 116 mils to the known point. So from down here at the center of my crosshairs, you go up 116, or you go basically, it's like what, 10, 20, 30, 40, 50, 60, 70. Well, I came up with 116 mils, so, well, that might be a boo-boo. That ain't no 116 mils. You don't even have that many mils in the freaking reticle. I guess I was tired. Okay, so that's supposed to be 116. It would compute to be 116 meters probably, because it's like 10, 20, 30, 40, 50, 60, 70 mils. So it's 70-something mils. That doesn't even seem close. Okay, so, all right. And, yeah, I'm finding it hard to figure out what the heck I was thinking right there. But it worked. I might figure it out, and I don't want to have to figure it out on my video. I don't know what I was thinking back then. So it's so we have oh duh. All right, so 116 mils from down here, because this is where it starts. This is the elevation. Hello, you're not measuring from the crosshairs. You're measuring from down here where the elevation is all the way up to the known point. Hello. Derp. Okay. So basically, we're looking at 200 and, oh wait, what's this? 218 plus 25 equals 243, and I didn't bother to give any information on what that 243 is referring to. Don't ask me. Okay. I'm going to go to this picture. This one was taken by, the credit for this photograph, I got it off the internet, but the credit goes to Derby Team, Kobe, and NASA. And basically this was a panoramic compilation type photograph where it basically gives us the galactic plane and the galaxy as you see it here. Now this one's even better for describing to folks what I call the galactic virga. When you're looking at this craziness going on down here, you see all this stuff flowing down around, draping down and swinging up and going up. These are the one parts of the galaxy that I'm referring to as galactic virga. And when you're looking at the galaxy on a galactic plane that is parallel to what we would consider the base of the ground on Earth, it pretty much means or shows us that our solar system is actually right up above here. It's above the turbulent hell down here along the galactic plane. So it's up here where it's nice and peaceful in the virga. Pretty damn close to the center of our galaxy, believe it or not. That's going to be shown down here in another picture, right? And so this one basically is telling us what the approximate offset is in angle from 0 degrees north, or the galactic true north in this case, and down here is a galactic pole true south, GTS, and the direction of the RSSP rotation, and that's going to be the raw solar system something. I'm not sure what the P is. Oh, raw solar system. I have it spelled out up here. Oh, there it is. Oh, raw solar system plane. That's what that P was. Gives us an attitude of 25 degrees. Hey, we're coming down here. And this has been so long, it's really difficult for me to have to. I didn't want to sit here and try to reanalyze how I did all this stuff. Sometimes things that I think about, it takes so long to think them through, and I have to go back and make so many changes. That's why up here you're looking at change 5. It only took me 5 changes to finally come up with the product I was looking for. And all right, here in our little word block, we've I don't know if you guys can see the dogs, but Boomer's getting a little uncomfortable there. He's decided he needs to sit up. Monkey's just laying down. Yeah, Monkey. The wife got Monkey a while back, when she was just a pup, and brought her home, and grandson looked at her and goes, "Monkey!" He thought she was a monkey. He didn't realize she was a dog. Seemed like a good name to give her, so we gave her the name Monkey. I like Boomer's name, because Boomer, like artillery. What's the sound of artillery? Boom, boom. You, Boomer? Hey, what do you know? We didn't even name the dog. We just went out and bought him. We looked him up on the internet and said, that dog's kind of cute. We can go ahead and get that dog. $700. Yep, and what they tell us, they say, yeah, his name is Boomer. You guys can change it well, of course we could change it if we wanted to, but hey, why do that if you already gave him a name? We're terrible at coming up with names. So, Boomer it is. All right, ain't that right, Boomsy? All right, okay. To adjust the ecliptic obliquity to the galactic plane, the OP must be moved 6.8 degrees east from the center of this view. Here's the center of my view. Here's my 7-degree bloop over to the east. Alrighty, and there's the galactic plane, and these two guys are, you don't remember. Alright, so now we're going to a more complicated picture that I have to explain. Alright, whoops, did I say that was a galactic plane? My bad. Okay, that's the ecliptic. Okay, so maybe we haven't figured out that's what these two yellow lines are. This is the galactic plane. Oh wow, it's been a while. Okay, so the ecliptic is right here. This is the Earth's relation to the solar system angle, and then here you have the galactic angle crossing the Earth, right? And the direction of solar rotation. direction of solar rotation. And I put the arrow to there. I had no idea why I put that there. Maybe maybe I need to make change 6, right? Like, okay, North Pole is over here. Oh, all right. Okay, this isn't north up here. Okay, the North Pole. Hey, the North Pole's right there where it says the North Pole is. Imagine that. I actually got something right. Direction of solar rotation. That's why that's there. I'm suggesting that the solar system is rotating in this direction on this axis, right, of the ecliptic. And then you have the North Pole there, and the direction of galactic rotation is going this way. You can't tell which this way is when I'm sitting there doing it both sides, right? So if I start over here and I go, the galactic rotation is going this way. There it is. Now I'm starting to be able to figure out what the heck my darn graphics are telling me. Direction to the galactic center is down toward the south here. Wait, that's not the south. South's over there. Okay, down to the bottom of the sheet of paper. All right, then this squiggly line going across here is basically the path and direction of how the SMEGAW, supermassive electromagnetic gravity wave from our galactic parent black hole, BH number 1, happens to strike the solar system as well as the Earth. And so it goes down, under, and sweeps out on the other side. All right. Ready. Now we're going to go down to the next one. Down here. Did I make any changes down here? I might have cleared it up a little bit. Oh, I've got this. This one here is showing us this little guy. Sunrise point is right there. That's all I changed right there, it looks like. Okay, next one. We're going down here. Oh, here's something to describe gnome point 1. So there's gnome point 1 right there, yo. Okay, here's that other one that I showed in another video. And with the credit, of course, to ESO and S. Brunier. ESO is a European space somebody or other. Observatory? I can't remember. Okay, and this one is a picture of the Earth. Earth at TDC. Okay, so basically I was taking photographs, well, not photographs, but, screenshots of the very top of Earth, getting it ready because I wanted to, crop it so that I could make it look like you're actually looking at the Earth at certain perspectives through space as you're flying by or something, right? And there I figured that one. Okay, then I figured it out there. Okay, then we went here. Then I put the sun over here, the RSS front elevation. Okay, so this is the RSS front elevation, which maybe I could bring that out so you can read it. And that's Earth right there. I don't know what he's doing outside the solar system just yet. But you see, I'm getting ready to put the solar system together here, right? So we have the sun at the center naturally, and this red line is supposed to indicate the maximum range of the solar disk, and then each of these red tick marks is to indicate the beginning of a month. So in between each mark is a 30-day period, or thereon or about, because we don't really have 365 days a year. That's why we have leap year, because we're always kind of a quarter of a day short. So 4 years later, you have a full day. Is that right, Boomsy? That's right. Yeah. That's right. That's right. Nope. Don't give me any wet willies, okay? All right. All right, fine. Okay, this is a better picture. I found a much better photograph of the sun and put it right there. And then I decided to go ahead and put the Earth around the sun, oriented in terms of where where Greenland would be. All right, then I'm coming down here. I know, isn't this great? It's so boring. Okay, that's just to really confuse the heck out of everybody. Earth at 24 degrees on a prime meridian, March view to galactic center. Okay, now while I'm doing all this, I ran into an issue, and now I'm not going to mention it because somebody might get mad. Anyway, the galaxy didn't exactly end up on the correct side of the solar system, and so I thought I'd let somebody know, but nobody ever answered me about that. Excuse me. Alright, okay, I'm figuring out the planet all over again. Alright, here we go. Oh, all kinds of crazy things going on right there, yo. Alright, so I had to figure out the, trajectory. The axial tilt of the Earth in relation to the Sun, here, all that good stuff. Alright, so where am I going? I'm going back down. Okay, Earth at 24 degrees in prime meridian, 1 degree north on polar axis to galactic plane. Raw solar system, angular momentum at 25 degrees. And the reason I'm saying raw solar system is because I felt like, our solar system needs a name. Like I mentioned it in another video. I mean, if you're flying through space, one of these days, if we're not wiped out by another impactor that's world class, we might fly far enough away from our solar system that if we have to stop by a galactic gas station or something and get instructions, how the hell are we going to tell them where we live if we don't even know what it's called, right? So hey, I live in a solar system, and there's only like 4 jillion solar systems out there, and they're going to be like, all right, this guy's a nut. All right, so anyway, momentum at 25, angular momentum at 25 degrees. That's right. X-axis, March view to galactic center. March view. Remember, it changes. Boop, 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 boop. Just depends. All right, next slide. We get a little bit more. Okay, now the next slide. Did I do anything between that slide and the other slide? Maybe. I'm going to skip that one. I'm going to skip that one. I'm going to skip those. I'm going to go down here. Boop. Hey, there's another one. So, here's this drawing that was done by someone, solarsystemnasa.gov, one of them guys. I really like this drawing too, by the way. So we have three black holes, ladies and gentlemen. We have the primary black hole, or the parent black hole at the core of our galaxy, and we have one black hole here and one black hole there. How do I know there's only 3? Because you can't physically get more than 3 in a line. If you have more than 3, then you end up with a hub. It's just the way nature works. So anyhow, you got them spaced equally apart right here, and so you have the 2 siblings out to the left and the right of the center. And sibling number 1 is what I'm referring to as black hole number 1, which is our parent black hole. And if you're thinking we're going to go all the way around the galaxy like this forever and ever, no, it doesn't quite work like that. It could be very turbulent for us. We would have possibly began somewhere in this region here, and we will end somewhere over in this region here, because the region between here and here, where the other black hole takes over, it could get ugly. We might not have a whole lot of, excuse me, Boomer, we really wants down. Monkey, you can get down too. Oh, okay. You could really have a lot of rough rides going on around there. And so here's known point 1 right there. And then I've got, a tangent. The tangent to something. Anyway. Now, we're going down right here. Oh, here we go. A little bit of a closer view. Here's the sun. Here's known point 1. Okay. And I'm figuring something out from the center of our galaxy to known point 1 and the tangent. And distance from known point 1 to galactic center is 0.76 inches. Hey, our galaxy really isn't quite as big as we thought. It's just not even an inch. Never mind. It's remarkable. Okay, here we go. Okay, so the distance from the RSS to galactic center is 1.01. The RSS is 23, and I know this is not the same RSS that the NASA uses, which is some kind of scale of something, or rate, or something like that. Okay. Now, okay, the RSS is 23.24% farther from the galactic center than known point 1. Not really sure what that had to do with anything. Okay? Okay. Now, we're out here, flipping around out here somewhere. Let me go back to this other picture. Was it that one? Go back to this one. We might, well, it just depends. I mean, if you're looking at the galaxy from this angle, and you consider where our sun is, and you picture the view going this way, well, where I pointed out our location in the galactic virga is extraordinarily strong to be possible. That's what I'm saying, right? So, if you're looking at it from this point of view, then it's different. It makes us look like we're way the heck, well, not really. I mean, if you look at it, right? Okay. Next one. All right, now see, this is how I had to squeeze the solar system together. So basically we went from a perfectly round solar system view, which was the frontal view, but then I had to give it a cant, and I canted it because we're not actually flying through the solar system, our solar system isn't exactly flying through the galaxy head on. No, I'm old, you know. Of course I have this within arm's reach. Doesn't everybody have their pills within arm's reach? I do. All right. Although it's empty, it's because I'm really terrible about filling it back up, and then I can't remember if I took my pills or not. Yeah. So anyway, well, that's how it works when you get old. And so here's the solar system, and it doesn't go to you like this. Nope. It's going to be at a cant. So now you see how that cant works. That's what you're looking at right there, even though it looks to be more like the shape of an ellipse than a cant. But that's what you get when you place flat round objects on a cant. They become ellipses. All right. Now we're going down here. Now I decided to, take all that stuff out and put my little red jiggity-doos in there and put the planet on it. And then I go to this one, and that's not the moon. That's just Earth out there floating around in space. Okay, that was what happened before Earth became... No, actually, it's just there. This is my perfect Earth, and these are all my subject Earths. Okay, now you'll notice that not only do you see the solar system coming at you like this at first, then we put a vertical 90-degree cant to it at this point, because 90 degrees because it's still up and down. All right, the cant is not 90 degrees. The cant is quite a bit different. And then we got to go like this. Boop. Oh, now it's starting to look like some of them flying saucers in the Ancient Aliens show and stuff. They're always kind of doing weird, flying, strangely odd ways, right? So we have this cant like this, right? It's going forward. So you have your forward edge here and your furthest outside edge over here. And as the waves from our galactic parent black hole are coming around like this, sweeping. So if I have it just like this, they're hitting the solar system as they sweep around. Maybe this is the better view. So my arm is the wave, sweeps, smacks, and swings down under and over. And at the same time that it's doing that, it's rotating our solar system. It looks really cool from my point of view. I don't know if you guys can see that. All right. But if you just look at a drawing on a two-dimensional sheet of paper here, that's what you're looking at right here, right? Okay, now we're going to go to the next slide. Boomer, I'm trying to talk to everybody. That's right. Booms, hang on. I just took you potty. You don't even ever drink water. How do you pee all the time? All right. Now we're going to the next one. Okay, so I can't just pause to... You got to hang with me, Booms. You hanging in there? Hang in there. Please excuse me. Boomer is being terribly impatient too. Shh. Thank you, Monkey, for being quiet. Okay, Monkey's usually the noisy one. All right, so here we are looking at it here, right? So this Earth here represents the summer solstice June 21. All right? And this isn't every year. Sometimes the solstice will occur at a different date, like anywhere like the 22nd or the 23rd, just depending on something. I'm not sure what. It changes sometimes. Axial tilt is at 0 degrees. Axial cant is at 23.5 degrees A. 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 Oh, 23.5 degrees, what? A. A means something, ladies and gentlemen. I'm pulling a brain fart. I think it's anterior. Thank you. Okay, axial cant, 23.5 degrees anterior. Anterior meaning the cant is farther away from us than it is closer to us. So if I have my arm as the axial tilt of any round object, if I want it to be 23.5 degrees interior, it's like this, meaning that the North Pole is closer to you, is what I'm saying. So interior means the North Pole is closer to you than the South Pole. Anterior means that the North Pole is farther from you than the South Pole. We tracking that? All right. Sorry I couldn't think of the answer to that sooner. Excuse me, I had to scratch my nose. That's how it works. All right. Now over here on the right side of my screen, you got spring ecliptic. As March 20, axial tilt is 23.5 degrees. Axial cant is 0. Notice the axial tilt and the axial cant change. They swap places. So you have, and then that's how it works, you know. And then you go over here to the autumn ecliptic, and you have September 23rd. Axial tilt is negative 23 degrees, and the axial cant is 0 degrees. And then in the south, in the south, at the bottom of our solar system, you have the winter solstice, December 21. Axial tilt is 0 degrees, and the axial cant is 23.5 degrees interior. So during the winter months, the North Pole is farther away from the sun, if like you were the sun. And then during the summer, it's closer to the sun. That's how we get our seasons. Okay. And you know, this up here is anterior. Down here is interior. And so June is up here. Now, here's the thing, right? The 2010 Eureka moment, and I'm connecting the 2010 Eureka moment with the extragalactic GRB, which apparently came from the direction of the Indus constellation, possibly beyond the constellation. The constellation being the furthest we can see. It basically came flying up. Now, visualize my cursor being behind our solar system. So it came up and went boom, right past our solar system. And while it did, it slowed down the rotation of the sun, and it slowed down the southern hemispheric rotation of Jupiter. So it had a greater effect, it appears, on the sun, because it was all about the same time frame. Now we're talking about a GRB that has a beginning and an end. It has a length. It has a PRF, pulsating repetitious frequency. That frequency is a pulsating frequency, and it depends on the length of that repetition of that light emission, or in this instance, that gamma emission. Okay, so as it's passing through, it's kind of like this linear bullet that's going by. So as the beginning of that linear vortex begins to approach our solar system, it already starts affecting it. And in this instance, it's so huge that it actually takes months to pass by. Yeah, month. It starts months. It starts affecting our planet in like March or something. No, maybe not that far back. It started affecting our solar system, I should say, very early on, and it did not affect the sun until June. Okay, June 21st, as a matter of fact. So that was when the eureka moment occurred. And when I say eureka moment, that's not me. That's NASA saying, "Whoa, there's a global tsunami on the sun." Global tsunami on the sun is where I derived the possibility that I confirmed my theories of vortical tectonics versus plate tectonics, and there's a very strong likelihood that asthenospheric tsunamis did in fact take place and are in fact quite plausible. It just takes enough energy to push our planet to the point of setting it into a state of worldwide liquefaction, which opens up these chain reaction possibilities. Okay, that's my point, and that's what happens, right? And so we get this solar system, or the solar system thingy. Now this is where I'm shrinking it down to fit onto some of my other graphics, and I don't know why I took that picture. Okay, we're going down here farther. Okay, I was getting a different view of the Earth. Okay, and here we go. I'm down here. So here it is. I'm pointing out the galactic virga on this very beautiful compilation that was put together by the ESO and S. Brunier. Okay, and here's gnome point 1. Doodle, you're being terribly rude. First it's Boomer. Now he's quiet. Now Doodle's screaming at me over there. Doodle, I let you out today. I even fed you. Yeah. All right. Yeah, I don't like to get into arguments with her because she always wins. All right. Now, here's the galactic heading. Here's the galactic center. And here's my conical center here. So as you notice, when I say conical is because typically it refers to the shape of a cone. But when you look at like things like conical washers and such like that, they're not cones. They're not pointed like this. Conical means that they're basically you have a round object like this, and somebody pushes the center up and makes it round like a plate, only the other way. So that's what we have. We have a conical center going on right here, and it's because of the pressure beneath from the universal jet stream that is what guides our galaxy through. So in the very same way, here's my solar system, in the very same way that the galaxy is rotating and pushing our solar system through space, this is now the galaxy. The universal jet stream is doing the exact same thing to our galaxies. Our galaxies flying through space just like our solar system is. That's right. It's like that. It ain't flying through space like this. Woo, woo. No, it's going through space like this. It doesn't fly like a frisbee. It flies more like a sail on a ship. All right. Pretty much rub that in there. Here's another picture. Oh, okay. I don't feel like explaining that one. Yeah, I don't feel like explaining that one. I don't know if I could. That's why. All right, so here we have this great something. Okay, and here we have another great something that looks just like the first great something. And here's a whole bunch of other somethings. Okay, so here's what we're looking at, right? On October 6, 2012, the slant was at 73 degrees. Somewhere. Sorry, folks, I don't know where the slant is anymore. When did I do this? Scan to computer is no longer activated. I don't know why it would have been activated to begin with. Oh, anyway. May 16. Oh, no, that's today. Was it this one? Whoops. Nope, wrong button. Oh, crap. All right, so days and 31 May 2019. Slant. I don't know. And this is talking about Earth right here, because these Earths are in their ecliptics, and this Earth is out here flapping somewhere. So basically, the Earth was right here, is what it's saying. That's what I'm saying. Here's where the Earth was when Mr. Morrow took a picture of the galaxy behind Mount Rainier. Whew, wow, that was hard. Okay, going to the next one now. Oh, hey, we got more stuff that looks like the old stuff that I just looked at. How about that one? Oh, there's the solar system. That's what the solar system would kind of look like if it was like flapping around up in there. In fact, that's where I would say it is. I think I pointed up to around here somewhere in the Virga. We're probably up here inside of this galactic Virga someplace, right? And then we have a whole bunch of stuff going on here. Earth at a 25-degree ecliptic. More complicated stuff. Spring ecliptic. Yep, got all that. Okay. And here's a face-on, head-on view of our solar system once again. The white foot shape on Earth is Greenland, in case you haven't noticed that already. The axial Terra clock was based on 2010, and the mechanical zero. This is my mechanical zero. All right, axial Terra clock is something I did something entirely different. I did it to determine. I was trying to figure out the solar system obliquity in relation to the galactic plane for 2010, June 20. I think maybe it was June 25, 2010. Was it June 21st or June 25, 2010, something like that. And because that changes every year, that's why it's the axial Terra clock. It's going to change, and once you establish one clock, then you can go backward in time to establish all preceding clocks to determine the Earth's position at times of certain events. Take, for instance, the South China Sea impactor. Where was the Earth when it got clobbered by that impactor? Yeah, that's what I'm talking about. All right, now we see a whole bunch of other weird things that I do when I'm trying to figure stuff out. And, yep, now we're looking at overhead elevation to Earth. I'm doing that right. Whoa, this is a big file. All right, going there. Well, maybe I'll skip all that stuff. Now we're back to looking at these guys again. We already looked at those photographs, pretty much. This one is where you're basically kind of like looking at the solar system as I was trying to describe with my solar discus pill bin, yeah, and it looks like that. And here's your waves coming around, sweeping, hitting it, striking it, and swinging down and under it. You see how that wave is crossing under it, almost at the same angle that it is sitting here, right? And that's how it's flying through our galaxy, ladies and gentlemen, at that axial tilt and axial cant. Oh yeah, this was my illustration of the black holes. So you have the parent black hole and the sibling black holes. Parent black hole is rotating counterclockwise, and its smeagons are what are coming out and rotating the others, because smeagons operate like gears. Solar wind pressure operates like solar wind pressure, like rolling a ball down the basketball court. It's like the basketball court floor, because that's how solid it is. I mean, so when you dive off of a diving board that's really high up into some water, if you do it right, you'll just go right through the water. But if you do it wrong, you're going to hit the water like a brick. Well, that's kind of what happens with solar wind pressure. Solar wind pressure, you can go through it, but when it comes at you head on and you hit it wrong, it's going to come at you kind of solid. So that's why the majority of our planets are rotating in the same direction as the sun. The coefficient of the coefficient of the solar wind pressure drag isn't what rotates the planets. solar wind pressure is what rotates the planets as they orbit the sun. And the planets that don't rotate in the prograde directions but may be rotating in retrograde rotations are doing so because they are further away from the gravitational influence, electromagnetic gravitational influence of the sun's disk, and they're closer to the electromagnetic gravitational rotation of the galaxy. So now the galactic gear-like operation starts to overwhelm the rotation of that particular planet, and so it goes in an opposite direction. So, but it's still buzzing around our sun, right? All right, now we come down here. All right, more stuff. Oh, hey, that's the end of that one, folks. That was my second one. Now we're going to go to pictures. Okay, here is my diagram. I worked all this morning. So this is the primary vortical diagram of Earth. Ladies and gentlemen, here's how the vortices work. So you have the Lake Victoria LV2 vortex right here, right? Actually, that's supposed to be LV2V. Wait, no, it's not. LV2, yo. All right, because it's Victoria vortex, so it's two V's. You know, I did it right. All right, here you have the Arctic vortex, the North Banda Basin vortex. Banda Basin is why you have B2, so NB2V. Then you have the POV, Pacific Oceanic vortex, and the Sapaliwini vortex, and then you have the Antarctic vortex. Okay, now if you notice, the Antarctic vortex is going in a counterclockwise direction. The Arctic vortex is going in a clockwise direction. And if you were to take the North Pole and flatten it out and take the South Pole, and my hand can't make that motion, like that. Now they're together. Now they're rotating in the same direction. So you have the Arctic vortex. Here's another example. The Arctic vortex is rotating clockwise. The Antarctic vortex is rotating counterclockwise. And when you put them together, they're rotating like this, going the same way. But if you do it like this, they're going opposite directions. Check her hold. You get the same thing when these guys get paired off. Okay? So LV2 pairs off with POV, and then you get these guys going in the same direction. Same thing with NB2V and SV. All right. Planetary rotation is prograde, which is going toward this direction. Well, if here's my... Okay. Planetary rotation is prograde. Follow my mouse going across the sheet from the left to the right. Then you have the force of galactic gravity striking the south pole of the planet. This is only in relation to these global views, not those. And then here you have two more Earths. And basically you have the coefficient of solar wind pressure drag. So the sun is basically, the solar wind pressure is basically blowing the continents. It's not really blowing them, it's dragging them, slowing them down from rotating at the same rate that the planet rotates, which means that they're basically moving westward. So that's why we have westward activity in our continents as we look upon the Earth. And solar wind pressure drag strikes the Earth in such a way that it spirals down from the North Pole all the way down to the South Pole. So it starts here, and you're going down, and it's going down like there, it's going down, or it's going down like this, actually, and then it comes down here, and it all hooks up right down here in a little curlicue. From the North Pole to the South Pole, spiraling down. That's what presents you with the continental virga. Continental virga? Continental virga. Pacific Ocean. Would be continental virga if it wasn't so messed up from an impactor. and Australia, which it broke away from Antarctica. Why? Because actually Antarctica was not necessarily as fine a circular entity as it is today. Well within pretty much that perfect degree window. And then you come over to, you start, so it broke off and started going up because of centrifugal force, started going up toward the equator. That is the only part that was originally part of Antarctica. No other part was part of Antarctica. Antarctica started at the same time that Pangaea started. All right, that pretty much explains that little mess. Then we're on to this one. Oh, the Earth's galactic flight posture. So here's like what I was explaining. I tried to get the Earth to be in the, basically at the angle you might expect it to see it, but if it was actually pointed, it just depends on your perspective. At what point in its rotation around, or its orbit around the galaxy, are you really going to see the nose of the Earth coming out like this? But you'll notice that in its flight, the North Pole, like the nose cone on a Blackbird supersonic aircraft, it's not pointed down. The Blackbird has them pointed down like this. The reason they're pointed down like this is because the nose of the aircraft is up here, okay? So as the nose of the aircraft, when it's flying, is flying through air like this, the jet cones are angled, and they end up, during flight, they're actually pointed straight ahead. Well, you don't really get all that cool stuff with Earth. Earth isn't quite that cool. Excuse me. So it's a little bit above the galactic plane, and above, parallel to the galactic plane, right? And it's angled at a point where it's just basically going around the circle. Like if my finger was the North Pole and here's a galaxy, I'm going around and I'm pointing in the direction, believe it or not, of my flight, going around the galaxy. Yeah, that's how that works. That all them gyroscopic properties allow the solar system, the sun, and the planets to have almost exactly the same axial tilts and axial cants that put them into a position to fly through space at a very high rate of speed, and aerodynamically or spatial dynamically, if it's space, maybe, I don't know. So the direction of the parent black hole, BH number 1, is going from the left side of my screen to the right side of my screen. Ooh, that was kind of a weird little one. There's a big explosion over there. No, okay. And again, I'm pointing out, I couldn't remember if I was going to be able to show you guys a slide pointing out galactic virga, so I put it in here. Okay, direction of galactic rotation is going from the right side of my sheet to the left side of my sheet. Then you have the universal jet stream basically striking the base of, which we already discussed, striking the base of the galaxy. And this one right here, oh yeah, there it is, galactic base. Okay, that's why it's more bulbous at the top than at the bottom, because there's a greater pressure at the base and less pressure at the top. There is pressure at the top, just less of it. All right, and this is our Ra solar system going on here, Ra, because it had to have a name. So I decided, why does it always have to be a Greek god? I mean, let's throw somebody else in there for a change. I would call it Ra, because I mean, that was the only one I could think of that had some kind of a relationship to do with the sun, right? At the time that I was thinking of it. And here's our solar base. Why? Because the Smeagol's are smacking the solar system from behind back here, and that creates the solar base. Higher pressure, lower pressure. Higher pressure, lower pressure. Higher pressure, lower pressure. All right, I think I pretty much covered everything on there. Isn't that great? Okay, cheers and jeers are welcome. Please remember to like and please do subscribe, because I actually have a lot of really good information here that's very, very evident. I don't know how to say that really. It's got a lot of evidence to it, right? You got to look at this stuff and say, hey, this actually makes sense. It does. Think about it. All right. And we'll go ahead and see you guys later. Maybe I'll let Boomer go outside for a minute or two. Or Doodle decided to get quiet. No telling why. All right. So I'm going to go ahead and shut down the tape recording.